Hey folks, in this video we're going to be talking about single replacement reactions. Bark, 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 bark. I would like you to be able to identify and define single replacement reactions. I would like you to be able to define oxidation, reduction, and also redox reaction. I would like you to be able to predict products for single replacement reactions, which you can probably do. And I would like you to be able to determine whether or not a single replacement reaction, when you combine these two chemicals, will actually result in a reaction using the activity series. And I want to look at some catfish. So let's get going. A single replacement reaction. We know this is a reaction where one free element replaces another that's part of a binary compound, two elements combined. And so here is our typical example. We have our free element replacing an element that's part of a binary compound. That element that's replaced then becomes its own neutral free element. So as I said, free element becomes a part of a compound, and this is going to be different for metals or nonmetals. Free metals are going to replace another metal, typically in an aqueous compound. So here is an example. We would see a free lithium replacing silver in this aqueous compound to give us now a free silver and lithium, part of that ionic compound. So our free metal is going to form a cation. Here, lithium goes from being neutrally charged to forming a +1 charge. Hydrogen is also cool because it can form cations as well and kind of pretend like it is a metal. So we'll see a molecule of hydrogen gas forming two hydrogen ions. Nifty. So here's an example of that. We might see, instead of lithium reacting with this silver, hydrogen reacting with that silver to give us free silver again, and in this case, nitric acid. Neato. So our free halogens or other oxygen are going to replace halogens, oxygen, or sulfur. So nonmetals, we're only going to really talk about the reactions of halogens and oxygen replacing other halogens, oxygen, or sulfur. And so an example of that is we might see fluorine replacing oxygen out of this ionic compound here to give us free oxygen and sodium phosphate? Sodium fluoride. What's wrong with you, Weingrad? Or here's another example. We might see chlorine kicking sulfur out of this covalent compound here to give us free sulfur and carbon tetrachloride. So that is cool. We can use nonmetals and they can replace other nonmetals in ionic or covalent compounds. So what's really interesting in these single replacement reactions is that our free element and the element that it's displacing exchange electrons. If we look at that first example with lithium and silver, lithium gains an electron, or rather loses, sorry. Lithium forms a lithium ion, Li+, where silver starts off as an ion, Ag+, and then is, at the end of the reaction, a neutral free element, just silver. And so this process of exchanging electrons we call reduction and oxidation. We'll talk a little bit about that more, I think right about now. So reduction is the process of an element gaining electrons. And this name comes from the fact that the charge of anything gaining electrons is going to be reduced, because remember, electrons have a negative charge. Hence the name reduction. If you gain electrons, your charge is reduced. Reduction. Oxidation, on the other hand, is when an element loses electrons. And so in that case, we're going to see our charge being increased. Now, this name obviously isn't as clear as reduction, but that name comes from the oxide. And an oxide is a chemical that's made of oxygen and some other element. And when a chemical loses electrons, often it will combine with oxygen. Or when it loses electrons, we might call that being oxidized. So a redox reaction, well, that's just a lazy way of saying a reduction and oxidation. So that's a reaction that involves electrons moving between elements. So that would include single replacement reactions, but other cool examples would be like when things rust or corrode, any burning or combustion involves electrons moving between different chemicals. And cellular respiration, the thing that keeps us alive as we breathe, is also moving electrons around. You may recall there's an electron transport chain that's very important for the cellular respiration process. Anywho, let's talk a little bit more about reduction and oxidation and actually look at an example here where we'll go through the states, or what we call the redox states, the charge for each of our guys. So magnesium starts off with a 0 charge, hydrogen starts off as a +1 charge, and sulfate starts off with a -2 charge. And after the reaction, we have electrons moving around, and we have hydrogen now with a neutral charge. Magnesium has a +2 charge, and our sulfate still has a -2 charge, no change there. Well, magnesium has been oxidized. We can see its charge increases. It goes from 0 to +2. This means that each magnesium ion, or atom rather, loses 2 electrons to form this magnesium ion. If we wanted to show this in a chemical equation, we would show that magnesium forming that ion and losing those 2 electrons. Those 2 electrons are being given away by that magnesium. On the other hand, hydrogen is getting reduced. Its charge is reduced from a +1 to a 0. So in this case, our 2 hydrogen atoms each grab 1 electron, and that forms 1 hydrogen molecule. So if we were going to represent that with a chemical equation, we would show our 2 hydrogen ions, sorry about that, our 2 hydrogen ions each grabbing an electron to form 1 molecule of hydrogen. And so sulfate just chills. Sulfate, as you noticed, didn't do anything. Its charge stayed -2. This is what we call a spectator ion. It's an ion that's not actually involved in the chemistry that goes down. It kind of just, I like to call them chaperone ions, because it kind of just brought that H+ to the reaction. We're going to see that this sulfate, we could change that out with another chemical without really changing the reaction. If I had used chlorine or chloride and replaced that sulfate with it, the chemistry between magnesium and hydrogen would stay the same. So spectator ions are something we may talk about in the future. Here's a dude with his hand. He is not being eaten by that catfish. He's catfishing that catfish. Here's another dude who's like, oh, he's really getting in there. And this lady, she's just like, yeah, I'm getting right up in this catfish. Look how happy she is. He looks surprised. And she's just like, got this catfish. Anywho, single replacement reactions. Let's talk about how do we figure out if they're actually going to occur. Like, I can mix 2 chemicals, but there's no guarantee that if I mix a free element in a binary compound that they will react. Well, we know that as I just said, free metals and ions don't always react together, but we can predict whether or not they're going to react using this thing called the activity series. So here is our activity series for metals, and we also have hydrogen in the mix because as we said, hydrogen likes to sometimes react like a metal. And this shows the most reactive to the least reactive. So the dudes up top really love to react. The dudes down on the bottom don't love to react so much. But let's talk more about that because that's not actually clear. The elements high on the series are very reactive when they are neutral. So if you have neutral lithium as a free element, that's very reactive. If you have neutral gold as a free element, that is not going to be very reactive. So the elements up top, when they are free elements only, are very easily oxidized. They give away their electrons very easily. They would like to form ions, especially out in nature. It's highly unlikely that you would find lithium as a neutral free element out in nature. It would love to react. Now, the elements low on the series are not very reactive when they're neutral. And this is really cool. I should say that they're easily reduced, or more easily reduced, but they're very useful for that purpose because they're not very reactive. You may notice that some precious metals, silver, platinum, and gold are down there. Those precious metals are in this list because they don't react. And they're good for us to wear if you want to wear a metal because they will not react with your skin and your body. Sometimes people have issues wearing nickel-plated jewelry because that nickel will react with their skin. And so they're also really useful for construction because you may know copper is commonly used in construction, and that's because it doesn't really react well with water or corrode. And as I said, jewelry is a common purpose for these metals, not so much mercury, but for these metals because they won't react with your skin. So how do we actually use this activity series to help us predict whether or not a reaction will occur? Well, you may have already guessed it, but these guys, as we said, if they're neutral, are very reactive. So we're going to first start by finding our neutral element on the table, on our activity series. We're going to see where is this neutral atom. Is it not so reactive or very reactive? And then we're going to compare our neutral free element to the one that it wants to replace. If the neutral free element is higher up, a reaction will occur. So anytime you have free lithium, since it's the highest up, it's going to react. But if you were to say put calcium as a free element in the mix and try to kick potassium out of an ion, calcium as a free element will not be able to kick potassium out of a compound because calcium is lower than potassium. Aluminum, if we were talking about this dude, aluminum can kick if it's a free element, it will kick any of these dudes out of a compound. but aluminum will not kick the ones above it out of a compound because it's not as reactive. So let's try and do some practice with this. Why don't you look at this list and try and predict, first of all, what are the products of these reactions going to be? Let's do that for starters. Pause the video and see if you can do these and make sure that they are nice and balanced. I've already balanced out one side, so it shouldn't be too difficult. Cool. Well, let's go through these together. Our first one, our calcium and our cobalt are going to swap places. And yeah, we're going to get calcium bromide. Down here, our chromium and our tin are going to swap places, and we'll have tin nitrate. Down here, magnesium and platinum should swap places. Pretty easy peasy. And we'll have platinum nitrate. And if you're confused about what charges to put on these ions, you can, oh, this table doesn't have it listed. We'll just keep going. I've established the charges on this side anyway. So here we've got aluminum swap places with nickel, and we've got iron swapping places with lithium. Nothing too spicy about predicting those products, but can you predict whether or not those reactions will even occur now that we've got them in front of us? Pause the video and see if you can use the activity series to predict whether or not these reactions will occur. Cool, we've tried that out. Let's go through them together. First one, I'm going to look at calcium, and I'm going to see where that is, and then I'm going to look at see where cobalt is, and see can calcium replace cobalt? Is it higher up? Calcium's up here, and cobalt's down here, so yeah, that reaction can totally happen. Great, let's move on. Tin, we're going to look at tin, Sn, and see is that above chromium? Is the free element above the one in the compound? Here's tin, Sn, and chromium is above it. So that means no, a reaction will not occur. Let's find platinum and magnesium. Platinum's way down here, so magnesium's not below it. Magnesium's way up there. Free platinum cannot replace magnesium from a compound. What about aluminum and nickel? Aluminum is here. Nickel is below it, so free aluminum will be able to kick nickel out of a compound. Yep, gonna happen. And lithium, we know, is our top dog, so if you see lithium as a free element, it will always be able to react. Yeah, dog, yeah. Let's do one, and let's talk about the reactivity of our single replacement reactions. Let's not do one. Let's talk about 4 really quickly. The single replacement reactions are going to work the same way. If we have our free element higher in the series than our than the element in a compound, then a reaction will occur. So why don't you pause the video and see if you can predict which of these 4 reactions will happen. Cool, let's go through them together. First, we've got bromine as a free dude. Oh, well, it already popped up. And chlorine, yes, and is in the compound, and no reaction will occur because bromine is below chlorine. It is less reactive. Our next one, we have fluorine. Fluorine's our top dog. So fluorine's definitely going to be able to kick bromine out of a compound. Yes, this will occur. Here are our actual products. And if we've got chlorine and iodine, well, chlorine is above iodine. So if chlorine is free, then we will definitely have a reaction occurring. And then we've got iodine and fluorine, iodine, or iodine, whatever. Iodine's down here, fluorine is above it. So iodine as a free element will not be able to kick it out. No reaction happening there. Oh, we got to balance this dude. Sorry about that. Well, that's the end of this video. I hope you feel good about looking at single replacement reactions, talking about what's happening there, explaining the processes of reduction and oxidation, and then also being able to use activity series to determine whether or not single replacement reactions will actually occur. Well, that's the end of the video. Ta-ta. Have a great rest of your life.